asking. Unfortunately not.
You like how we got to the point of the semester where we're also like comfortable raising our hands when I do, but like most people keep talking when they do it. Train half of it, like it's muscle memory. We are in the last quarter of the semester now. You've come so far. I don't know exactly how far you've come because I haven't got a chance to look at the exams yet for exam 3. But I'm hoping it's really, really, really good.
We all got it.
I will be grading them tomorrow. I'll try to have the grades posted by the end of the day. Tomorrow night. And I should post the answer key too, so you can go look at it. But I'll give exams back on Wednesday, or if you come by my office before then, you're welcome to pick up your exam anytime after tomorrow at 4, maybe? I don't know. So anytime Wednesday you can come by and grab it, or I'll give it back. I will have office hours on Wednesday, so if you have any questions about the exam, you can come by then. Normal time, 3:30 to 5 in ETAS 125. I was very happy to see the week of the exam. There were a lot of new faces at office hours, and it gave us an opportunity to kind of answer a lot of different questions that people with different perspectives had. If you haven't been to one of my office hours, it's not one of these things where you like line up and you ask one question at a time. It's like we all come together and we bring up questions, confusions we might have, and then we work through them together. So it's a bit like class, but more focused. So if you have the opportunity to make those. Also, if you can't make those, if you have work or you have children or something, I've been sending out a Zoom link, and I should send that to the whole class, because a few people have asked for it. So I just set my iPad up during office hours, and you can kind of be part of office hours. So if that is useful, you can do that, and you just make sure you're muted when you're not talking. And then you could be at work, and you could just have the earbud in your ear and hear people are talking about, or you could do whatever works for you. So I will try to remember that. Can someone volunteer to send me an email to send that out? Great, Chris. Just send me an email tonight, just now, and just say, Zoom link to everyone. Zoom is the software, and so all of you can be involved. Just make sure you mute the audio if you join.
How do you spell it? Z-O-O-M?
Yeah, like Zoom. Okay. So for tonight's class, question? You can use the app. It's a little easier functionality, but you can just use it right in your phone or your computer. If I was going to do it and I knew ahead of time, I would download the app. It's free. You don't have to pay for it. We have a subscription as part of the STEM Education Center, so we can have as many people as we want. And if you talk, then your screen will come up as the main one, and so you can use video and audio. It's a really nice software. And I'll have it facing the whiteboard, so I can put your stuff up there or whatnot. Okay, so today in class, what we're going to be working on is building off of different types of reactions. There was no primer today because we've already done a bit of that. So there is a primer for Wednesday's class because we're starting on new material. So if you have not already, go ahead and look at this reaction. We're going to go through that whole list on the front page and determine what type of reaction those are, types of reactions. And if you look at the top under question 1, it says for each of the following reactions, determine or go through that list of 3. So for now, just go ahead and click in what type of reaction is, but I'm going to ask you for all of these to write the net ionic equation. And then if it's a redox reaction, we're going to say what's oxidized and what's reduced, and that there's information on the back that you can use if it's an acid-base or a redox reaction. What? We have 35 responses. Not sure if that's frozen or not. Anyone need more time to click in what type of reaction this is?
Oh, that's frozen.
All right. some reason the number of responses is changing, but nothing else. So I'm going to go ahead and close this. And then maybe that'll update. Nope. I have no idea what y'all answered. But I did see earlier on that we had some people say that this is a precipitation reaction. Why might we want to say it's a precipitation reaction? Because what? There's a product that has a solid. That is one of the components of a precipitation reaction. Does that mean that this is a precipitation reaction? Shelby?
No,
We didn't start with two aqueous solutions. It is not a double displacement reaction. So what type of reaction did you say that this one is? So how do we know it's a redox reaction? You want to finish that one out, Shelby? The charge has changed. What's the charge on this initially? There's no charge. What about on our silver? Plus or minus? Plus 1. That means the chlorine is minus 1. Copper on the right side.
2 plus.
And then chloride,
Still
and silver. So what we're looking for is, was there a transfer of electrons from the left to the right side? So our copper goes from 0 to a plus 2. Does that lose or gain electrons? What do you think? Is it losing or gaining electrons?
It's transferring.
So I want you to talk to your neighbor for a second. Determine which one, if either is losing, which one is gaining. Think about what their charges are before and after the reaction.
Even balanced.
All right, so let's raise our hands if copper is gaining electrons. Copper is gaining electrons from left to right. Raise your hands if you think copper is losing electrons from left to right. Ooh, we're split about 50-50. Who wants to argue their case? Lena?
I think copper is losing electrons because if you have more protons than electrons, you're going to have a positive charge, whereas if you have more electrons than protons, you're going to have a negative charge. So it had to lose electrons in order to have a positive charge.
So when it starts out, it has the same number of electrons and protons. Afterwards, what happens to the number of protons?
Is this the same amount of
It's copper. Copper means it has how many electrons? There are protons?
29.
Copper means by definition it has 29 protons. So it's still copper afterwards. It was copper before, so no change in protons. So to get a positive 2 charge, it had to have lost 2 electrons. So that one is loss of electrons. Let's look at the silver. What happens to the silver? Raise your hand if silver gained electrons. If we think silver is gaining electrons from left to right. Okay, we have about a third of the class. Raise your hand if you think silver is losing electrons from left to right. Okay, we had more vote for the first one that is gaining electrons, but I didn't have the whole class. So on the left side, what's the charge? And then on the right side?
No charge.
No charge. So same number of protons on the left and right side, but here it has 1 fewer electrons, here it has the same number. So it gained electrons from left to right. What do we call it when it loses electrons? What's the fancy chemistry term for that? Look on the back of your page. Make your own decision. And what's it called when something gains electrons? Okay. So there's, you see the moniker that I use? Is that moniker? I don't know what it's called. Leo the line goes grr. Do you see that? I think it's on the back page, right? very top right here. Leo, LEO. Losing electrons is oxidation. Leo. The line goes GER, gaining electrons, reduction. So that's what I use. There's oil rig is another one people use. Whatever you use to remember what is called oxidation, what's called reduction is fine. On the final exam, that is one of the things you'll be tested on, is can you identify what type of reaction something is and then determine what's oxidized and what's reduced. So in this case, if I asked, what is being reduced in this reaction? What would we say?
Silver.
What is being reduced? Talk to your neighbor. If I say, what is being reduced, or the same thing with oxidized, what are going to be your two answers for that? Go ahead and talk to your neighbor and try to determine how we answer that question.
Otto replied, thank you for the email.
Two of them.
Otto replied, thank you for the email. I am not out of the office until Monday.
You just emailed me, that's the message you got? Okay. Okay, so let's see who can be really specific and answer these questions. Can I get two volunteers? Can I see two hands? Please. Chris is going to answer one. Who wants to answer the other one? Robbie, do you want to try? One of them? Rachel? Can you answer one of these for me? You pick. You go first, and I'll have Chris do the second one.
Since the copper loses the electrons, it's oxidized.
Okay, so you would answer the second question that copper is being oxidized. Is that right?
Yes.
Okay. And Chris, how would you answer the first one then?
Because silver is gaining electrons, it's being reduced.
Okay. One of those two answers is correct. One of them is almost correct.
Oh, F.
So there are two types of copper, and there are two types of silver in this reaction. We need to be specific. So when we say copper, we imply copper zero. So Rachel's statement was correct. I don't know if she intended to be that specific. But if you say copper, copper solid is the one that is being oxidized, then that's okay. So I'm going to change color here.
Silver one.
So then, Chris, can you modify your answer for what is being reduced?
Silver one is being reduced.
Yep, silver 1, or if you wrote it out, you'd say Ag plus aqueous is being reduced. Because we just said silver, well, I mean, yeah, the things on the right aren't being oxidized or reduced. They're the products of it. But we want to be really specific and say that one of them is gaining electrons, one is losing electrons. Are there any spectator ions in this reaction? Write down on your piece of paper what your spectator ions are. And then go ahead and write the net ionic reaction. Maybe I'll pull that up right now. I think that's the next. So there's no clicker for this net ionic reaction, but please write it down under part A. I guess it's what, A2, whatever you call it. If you get stuck, call one of us over. Got 5 people to help tonight.
Bless you. Thanks.
chlorine is a, yeah, I'm saying chlorine is a spectator, and then I'm writing that as Cu solid plus Ag plus aqueous, no, Ag plus. Ag plus aqueous, because see, look, AgCl is aqueous right now, so that means that Ag is also aqueous. Yeah, but I'm talking about the one on the silver. Yeah, and then yeah, the silver solid is on the yeah, the product. So I'm just putting it like this, where it's not on this side, but it's including this one. Oh yeah. So it's on this side because obviously copper changed states, right? So it's participating, and also because it's important for the background. Yeah, it's not a spectator because it's part of this product.
Right side.
Unless the correct answer is actually just Cu2 plus aqueous. That could be the correct answer. Yeah. That could be like this instead of this, but I'm not sure. Yeah, the chlorine didn't change, so it would be down from this, but I'm not sure it's because it's attached to participating reagent.
That's great.
That it gets written down, so I'm not sure if it's just leaving Cu2 plus aqueous or CuCl2 aqueous.
Okay. Do we want to go directly to the net ionic, or do we want to do total ionic first? Do we want to talk about spectators? Where do y'all want to go? Do all of them. Sure, you can volunteer to read me whichever one you'd like. Do you want to take a stab at the net ionic, and then we can kind of back it out from there? Or do you want to think about any spectators there might be?
Okay, I think the spectators. Well, okay, I thought the spectator ions were the ones that don't change.
Spectator ions are the ones that don't change. What about them doesn't change?
Their state.
Their state and? What else about the spectators doesn't change besides the state?
The charge.
Yes. So is there anything that's the same charge and state on both sides of the equation?
Okay. Some of them.
Did you say some of them?
I said some, none of them.
None of them. Does everyone agree? No spectators. What spectators might we have? Cl. Okay, Cl minus, so chloride ion. So if we go into solution, this silver chloride breaks down into Ag plus aqueous and Cl minus aqueous.
So the two doesn't matter.
The question is how many of them there are. On the right side, this, when it's in water, is Cu, what charge? It's 2 plus aqueous. We know it's copper 2 because there have to be 2 chlorides to make the neutral salts. And 2 Cl minuses aqueous. So there is one of them before aqueous. There are 2 of them afterwards aqueous. So are they gremlins? They multiply when they hit water? So what's wrong? We forgot to balance the reaction, and that might have helped us think about it. Okay? So we can either balance before we do the net ionic, or we can do it afterwards with the net ionic. So how can I balance the reaction as it's written up there?
A 2 next to AgCl aqueous, and then a 2 next to Ag solid.
Okay, so we could have put those 2's in there first to balance. That might have helped us a little bit. And then we'd say, okay, well, I have chloride as a spectator on both sides. So then can someone read, can I get a volunteer to raise their hand and read the net ionic once we've gotten rid of those spectators. Okay?
Copper solid plus 2 silver aqueous.
Silver ions, aqueous.
Silver ion. 2 copper ion. 2 plus
Copper 2 ion would be another way to say that, sure.
aqueous plus 2 silver copper.
Fantastic. That's our net ionic equation. How do we feel about that? So it's important this is something that I had a discussion with as I was walking around. We're at the point of the semester where I'm not going to tell you it has to be balanced anymore. You know that any chemical reaction has to be balanced. It has to be balanced for charge, it has to be balanced for the number of elements, it has to be balanced for mass. Everything has to be balanced. So I didn't say that for the net ionic. I didn't say the balanced net ionic. I said the net ionic. And it's implied that you have to do the balance. Otherwise, it would look really weird, right? That we would have 1 silver ion starting and 2 in the end. Doesn't look good. Doesn't feel good as a chemist. All right. So that's what we're going to do for the rest of these. So let's answer some really, really quick clicker questions to see if we're on the same page about this. So I'm going to put these up on the screen. This is about that exact net ionic equation that we just made, that Rakaya said out loud. So in that net ionic reaction, the reaction we just talked about, copper is losing or gaining electrons. Let's do like 10 or 15 seconds per question. Couple more seconds. All right, closing out. So a majority of the class said that copper is losing electrons. I agree, because we're going from copper 0 to copper 2 plus. So then based on that, we are defining it as copper is being trying to decide whether this is worth our time. Let's do this on another problem. Does that sound better? Kind of already written all this down. All right. I'd originally planned on going through this differently in my head. So, majority of the class is saying that because it is losing electrons, it is being oxidized. So then we can kind of do the same thing with silver. Gaining electrons being reduced. We talked through that. So what I want you to be able to do today is look at a reaction, and we're going to do this on the final exam again, determine the type of reaction. And I want you to be able to, if it's an acid-base reaction, I want you to be able to predict the products. If you're told it's an acid-base reaction, I want you to be able to identify if it's a redox reaction, what's being oxidized and what's being reduced, kind of what we just did. And then we're going to bring in the terms agent, a reducing agent and an oxidizing agent. So we'll come to that in a little bit. So what we just looked at and what we saw is you have a oxidation happening and a reduction. Can we have one of those happen without the other? Can we have just someone accepting electrons? One of the ways to think about it is Walmart is very rich. Could they have gotten that rich without getting money from other people? So the idea is a transfer. It's a transaction, right? A transaction means that something comes from one place, it goes to the other. So if one thing loses electrons, it can only do so by having something else gain those electrons that it's losing. So if a reaction is going in this direction, where it's losing electrons, it becomes less negative, or you could say it becomes more positive, any of those are considered to be an oxidation. Doesn't mean that it has to start with no charge and become positive. It can start with a negative charge and become more positive. Any of those count. On the opposite hand, if that happens, then something has to go the other way. A pairing has to be able to be reduced. So let's take a look at some other reactions and see if we can identify acid-base versus redox versus precipitation. So what about reaction B? What do we think this one is? And if you figure out which one it is, go ahead and start writing the net ionic reaction. And if it's oxidation reduction, then identify what's being oxidized, what's being reduced. Why don't you check with your neighbor? We have just over half the class has responded. With what type of reaction? Go ahead and check with your neighbor.
Stores information there.
Okay, go ahead and submit your response. Closing out, need 5 more responses, 3 more. All right. We are majority saying no reaction. Does anyone feel strongly about that or one of the other reactions, other types of reactions? Majority of the class is wrong. So what type of reaction is one of the other 3? Talk to your neighbor. Which of the other 3 types of reactions is this?
The majority. What would majority?
Because
No, it cannot be. It cannot be.
balance it,
Okay. So then why is it redox if that's your answer?
Because everything else is going.
Okay, so beside process of elimination should also be positive with the one you think it is.
Isn't that iodine?
Go ahead and revote. Revote. The answer is not D. It is a reaction. So vote which type of reaction you think it is.
but the thing is that one of them
We thought we were getting an easy one, but we didn't have to write the ionic equation. We're happy.
bromine is neutral.
And before I show the responses, go ahead and write the net ionic reaction. Remember, that means if it's aqueous, you separate it into its ions. You get rid of any spectators. That might help you identify why this is a reaction. Okay?
Supposed to be something. That's ammonia, isn't it? That's there. It's what it is.
What's the charge?
Positive. They just took right a second.
It's neutral overall, right? So what's the charge of each one?
That's still positive.
All right. Can I have a new volunteer to read me their net ionic equation? New volunteer. Jocelyn. Any charge on that? Did you say again? Br.
And I do a plus 2 charge.
And then reaction, the I with the plus 2 charge. It's still AG. Plus BR. That's neutral. And it's aqueous.
So we have a few things here that I might disagree with. And what becomes challenging about this is some things you haven't seen. So I'm glad that you pointed some of those out. The things that you have seen, though, let's drill in on those first. What do we think about this over here?
It has a charge.
Why do you think that this has a charge, this I?
Because it's attached to something that has a charge.
So this is our polyatomic ion ammonium. We know ammonium has a +1 charge. If we find I in a salt, it's going to have a -1 because it's in group 7. So that is going to be I minus. Okay. The one that you might not be so comfortable with is when something is, we call it elemental. So it is a molecule of bromine, and bromine forms molecules with itself. So there's 2 of them. It's a diatomic. Di means 2, atoms, atomic. So diatomic molecule. What's the overall charge of that Br2?
It's not negative.
Neutral.
What's the overall charge?
Neutral.
0. There's no charge. So what is the charge on each of the bromines?
Neutral.
0. So if that's Br, then that means that it's a molecule, it's not ionic, it doesn't separate into the individual BRs. If it was, normally if we find Br as an ion, if it's an ionic compound, it's going to be -1. We can't have 2 BRs with a -1 charge, so this is actually a molecule. If we do the Lewis structure, that's Br2, not ionic. Okay, so that has no charge, and it's a molecule. There's 2 of them together. It just means it's floating around in water. So then, can I have someone else help me on the right side? What do we need to modify about the right side? Yes.
Iodine does not have a charge. And then the Br.
Anything else different about the I?
Oh, there's 2.
It's a molecule with 2 I's, just like the Br2 up here. And then?
And then the Br has a negative charge.
Okay. So this is a curveball, intentionally, something you haven't seen before.
So since the BR and the I are separate right there, you don't balance the equation because they're by themselves.
So that's the last step we would have to do to get the net ionic equation. Do you want to finish it off and tell us how to balance it?
It would be. I guess just at the very end, it'd be 2 BR negative.
Anything else?
Oh, well, you have to do 2I.
Great. That is the net ionic reaction. So now, does this help support what type of reaction you thought it might have been and why? Eleanor, what do you think it is, and how does this help you identify that?
We see that, one sec, iodine, crap, my brain second. Was it oxidized? Wait.
So it goes from a -1 to a 0. So is that losing or gaining electrons? You can have a shout out from the class if you want. Losing or gaining electrons for I? Losing. Okay. Losing electrons is oxidation. Leo goes Gert. And then bromine, bromine.
Oh, you're asking me?
Sure.
Oh, yes, and that gained an electron, so it was reduced. The bromine aqueous.
Can we start to see now with it written out with the net ionic? We can see the change in number of electrons that each species has. Okay, so let's go through, now that we have the net ionic, let's go through these steps because we kind of talked through them quickly. So we're going to go ahead and close that out. So in this redox reaction, we can see that iodine Click one of these. Is it losing or gaining electrons from what you have in your net ion? And the net ionic is up here at the top, just to make sure if you didn't catch it. We can do another 10 seconds for this question. Check with your neighbor if you want. Please check with your neighbor. We're not in agreement. Check in with someone around you. And if you disagree, make sure you say why. All right, closing out. So our I from left to right is losing electrons. It starts out negative, it ends up less negative, meaning that it gives up electrons. So what are we going to call that? Go ahead and submit your response. Is that oxidation or reduction? Couple more seconds. Julia, what did you say for this one?
I said it was oxidized
Why?
because it loses.
So our definition is losing electrons is oxidation. Leo, LEO. Okay? So then let's look at the bromine. In this reaction, bromine from left to right, what's it doing?
What is that?
It's the sonar.
It's the worst.
Make sure everyone's around.
Why did you choose that as a text note?
It was
Couple more seconds. Closing out. Okay, so here's the reason I'm kind of happy. Even if you're kind of lost right now, everyone picked that answer. Why? Why does that make me happy? Because what? Okay, so some people are figuring it out and they got that. But the other thing is that you realize that even if you don't know what the heck is happening with the charges, you're like, well, in order for one to happen, the other has to happen too. At least that's how I'm reading that response. So, because the top thing gained lost electrons, then this one has to lose them. So even if you have no idea what you're doing, but those two, you know the relationship between them, hopefully. So then what do we call that? When something gains electrons? Couple more seconds.
Why do they call it reduced if it gains something?
I was literally just like the words you said.
And we're closing out.
It's like the opposite.
I'm going to... Oh, dang it. I was hoping to get to you before you got back in. Okay. People got to mess with me, huh? Well, just for that, I'm going to click the right answer so it says you got one wrong. Okay. There's a really good question. Why is it called reducing if it's gaining electrons? So the original term came before we really understood subatomic particles. We didn't know protons, electrons, and neutrons. We just knew that if something was exposed to oxygen, like iron is a really good example. If we have an iron nail and it sits out exposed to oxygen for a long time, what happens to it? It rusts. Rusting is an oxidation process. So oxidation was referred to as exposed to oxygen. And it turns out we ended up figuring out that it's a process that happens a lot more than just with oxygen, so we broadened the definition to say it's about the transfer of electrons. What about this next reaction? Reaction C. Where's mine?
I didn't get another
And if you're not sure what kind of reaction it is, write the net ionic reaction.
Acid.
Squad.
And hydrogen.
All right, we have 38 responses. Kiera, you responded? Great. Okay, we got 39 now. All right. Did everyone get a chance to do the net ionic? Okay, so maybe let's just say type of reaction. Can I have a new voice explain why they chose the type of reaction they did? And then we'll do the net ionic right after that. Donald.
I said it was an acid-base reaction.
Why?
The hydrogen gets added to the HO, H2O, and it came off the HCl.
So it starts here, it ends up pairing up with this, and we get the transfer of a hydrogen ion, an H plus ion, which is the definition of an acid base. I agree. So I'll give you another 30 seconds or so to write out your net ionic reaction. Think about what's the same on both sides. Remember, if it's a molecule, if there's no ions in the molecule, we don't separate it. Do I have a volunteer that wants to write the net ionic? Look for you.
Oh, that's big.
You don't run out of space.
Oh, really?
It's really big. Want to do it a little bit smaller?
Yeah. I'm gonna write it right here.
Because it's so different. No, but we haven't given you anything. Molecular diatomic, so thank you for being willing. Okay. All right, we have a brave soul that volunteered. So Rakaya was willing to write her net ionic up here. How do we feel about this net ionic equation?
He's not quite Pearson, assuming it's right.
I get Savastier giving a thumbs up. How are we feeling? Dustin, you have a question?
There's already two H's on both sides, so why did we put two before? It's a polyatomic ion.
Also, we got 20 hydrogens.
So I guess the question is, right now, is it balanced? So right now there are 4 hydrogens on the right, 1, 2, 3, 4 on the left. There are 2 oxygens on the right, there are 2 on the left. So technically it's balanced. Is there anything we can do to make it a little bit better?
Divided by all those twos.
Yep. So if there's a lower common denominator, we always put that there. So I agree, except for I would just remove the 2's. And then that is balanced, and it is simplest balanced formula you can have. Lena?
Why do we keep the H2O together?
So that's exactly what I was referring to earlier. So remember from the days when we were drawing out molecules, this is not a salt. So we're not going to draw something that's a molecule that's not doesn't have any ionic bonds. We're not going to separate that when it becomes aqueous. The question might be, well, what about HCl? If you drew the Lewis structure of HCl, you would draw this. What we have to remember is there are certain molecules that have really polar bonds. And one of the things that's a dead giveaway is if we have an H moving in the reaction, we know it's because that H must have acted as an H+. That tells us that it was a Cl-, and that's an ionic compound when it's in water. So it's kind of about recognizing an acid-base neutralization reaction. Jay, that wasn't your question, though, was it? What was your question?
Okay, so I get why you took off the twos, but doesn't it make it like when you're just looking at it, not in the scientific, smart people who already know this, like just looking at it, I'm like this, like you need the two to know that it's like the twos in front of the ions to know that they're like they match, like they're balanced. Or do you not?
So if we look, maybe it would help to simplify if we look at the top reaction. So I'm going to clean it up a little bit. What are the spectator ions in that top reaction? Potassium is aqueous on both sides. Anything else? Chloride is aqueous on both sides. So that means that if this was Cl-, that had to be an H+. If that's hydroxide, then it is balanced kind of as it is. So just sometimes going through a couple different times in different ways helps show that. Okay? So, spoiler alert, whenever you have the most common acid-base reactions, this is a really common thing to have as your product. It's water. Is that the only time? Do we always have H+ plus OH- gives water? I think I showed a reaction last week that wasn't that. So be careful. Sometimes we have the transfer of an H+ that does not just do this. But if we see this as our net ionic, for sure it's an acid-base neutralization. We're taking something that we call an acid, we're combining it with a base, and they neutralize each other and form water. Okay. At the bottom of your back page, question number 2, I guess it's in the middle of the back page. I have, now that we've done an acid base, I want you to practice writing the products for a neutralization reaction. So write out the reaction when these two combine in an acid-base neutralization reaction. Do I have to tell you these to be balanced?
No, but you kind of just did. It's helpful when you do.
That might be
Will make our life easier if you did.
Like if you don't tell me, I'm probably not going to do it.
It's neutral because, look, it's full of salt.
haven't already, check with the person around you. See if you have a similar reaction. Focus on any differences you might have.
Who knows? Somebody could have dialed in. I have no clue. Yeah. But yeah, I remember my car did the same thing, but I had a leak. Yeah, I don't know, it wasn't dry enough, it was just like there was a leak in there, and I forgot how I cleaned it out, and I just cleaned it out, and it stopped. So, because it was like the fan was in the past beside me. Yeah, pretty much.
That's what homework is.
Yeah.
You're gonna be scared.
No, take it too far. I don't know why it's homework because
ATI, I think it was part of it.
I never do that. But you don't
Okay, I don't want to clip this in for a second. I just got nervous.
That's just it.
Now it's a clicker question.
What the heck?
I choose number 2. I mean, number 4. My bad.
Okay, 28 responses. Go ahead and check out these answers and see which one of them you think you agree with the most. 34. All right, I'm going to go ahead and close this out.
No, we got the same thing.
So we have a mixture of responses, but 4 is our most popular response. Would anyone like to explain why they might have picked that? Andrew? Did you pick 4? And if so,
I did.
why?
Well, so we have to have 2 waters.
Why do we have to have 2 waters? It's a really straightforward, clear statement. You knew that for certain. Why?
Because of hydroxide, there are 2 hydroxides, and when that
So I'm going to build off of what you're thinking, hopefully, and saying, is that whenever we see a barium hydroxide or something with a 2+ ion, we have 2 hydroxides, we think about, if it's aqueous, it means it goes in water, and it dissolves into 3 total ions. Remember last class, that was one of the things we kind of focused on, is how many ions does it separate into. So that means that if this is part of a neutralization reaction, how many H pluses will it consume? How many H pluses can every OH minus react with or consume? You can only take up one of them, right? So if we have an H plus floating around, that one of those 2 OH minuses is going to grab that. But if we have a balanced equation, we have to show that there's 2 of them. Each one of those forms a water when an OH minus and an H plus come together. So we end up with H, OH, liquid for each one of those, or we can just write H2O, liquid. So hopefully when we start to look at neutralization reactions, it's kind of easy when there's a hydroxide. Anytime there's a metal and a hydroxide, it's going to make water with that hydroxide. Because we know it's a transfer of an H+, one of these is going to combine with an OH-, and we're going to form water. There are a few other acid-base reactions we saw that is just the transfer of an H+, but this is the most common type. So then if we know we form 2 waters, that means we have to have 2 H+, so where does that influence the reaction? How do we make sure there were 2 H+?
You put a 2 in front of the HBr.
We needed 2 HBRs because every one gave off 1 H+. And we just made sure the rest of the reaction was balanced. Questions? All right, I want to go back to... So this is the kind of question that I will give you. I could give you this on an exam, but I wouldn't just say, what happens when HBr reacts with barium hydroxide? I would tell you it's a neutralization reaction. So then you know it's a transfer of an H+, and that lets you hone in a bit more. Questions on that? So do we have any spectator ions in this reaction? Oops, wrong type. So this is a multi-select. Type in the number for any spectator ion that we have in this reaction. Check with the neighbor next to you once you entered your answer. Couple more seconds. Keisha, which ones do you select? 3 and 4, these two. So if we go up and look at the reaction, everything that's part of this changed. So these two are spectators, which is those two. Same state, same charge on both sides. Okay, that's the majority of the class answer. All right, so let's go and look at some of the other reactions. So flip back to the front side. And I'm going to give us, we're going to try to answer these next few questions to give us like 3 or 4 minutes for the questions at the very end of the back. So we'll try to go quicker through these. So if you're stuck, flag one of us down. Select the type yourself, check with the name.
Are you sure it's from here?
On this side, on this side.
Because, you know, you see it's enough to move things, because the whole car's going to fire. So it could just be a piece of plastic.
So notice that there's a typo on your sheet when I transfer this by hand. The reaction on the screen is correct.
Yeah.
Yeah. It's not AG, it's G. All right, a couple more seconds. Okay, closing out. All right, is this no reaction?
No.
We know that we have aluminum starting here, different than it is there. So it's not no reaction. So what type of reaction is this then? Precipitation? We have a solid in the product. Is it precipitation? No. Don't fall into that trap. There's a solid in the product. That does not mean it's precipitation. One of the things that's there. So then what type of reaction is this, Ada? You said it's a redox? Why? So the chlorine starts with what charge? Does everybody agree? -1 on the left side?
No.
If it was -1 and there were 2 of them, it would be a -2 molecule. But it's 0. So they have to be 0 each. What about the aluminums? What's the charge on aluminums on the left side? Also 0. Wait, so then we can't have a transfer of electrons, right? What's the charge of chlorine on the right side? There, it's a metal and a non-metal, so that's a -1. So that means that aluminum is what charge on the right side? So on this side, it's a metal and a non-metal, so that's a salt. Neither one of these are salts.
Can you explain it again? Because I don't get how the left side is 0.
So if we have anything elemental, meaning it's just with itself, either as a metal or as a gas, it's no charge.
Okay.
And we can see that because there's no overall charge here, and there's two of them, so it couldn't be a -1 because it would be -2 total charge. It's not. We would have to show that charge, and it's not there. So here's a kind of an interesting, different redox reaction because we do have the transfer of electrons. Something becomes more negative, something becomes more positive. So then, which is the oxidizing agent? You might want to read on the back.
Oh, what, my bad. It's reduction. My bad.
Let's do another 15 seconds. Read your definition. Oxidizing agent, reducing agent. It's on the back. Closing out. Okay, so it's a process. Let's think about this. So first we're going to say, what is...
The wrong question.
Let's say what's oxidized and what's reduced. So can I have a volunteer to say what's oxidized and what's reduced? New voice. Brendan? Bradley. Sorry.
Aluminum would be oxidized because it is losing 3 electrons when it combines with chloride and
Chlorine,
chlorine.
because it's not negatively charged. Great. Okay, so aluminum goes from 0 to +3. That means that it is losing electrons oxidized. So then what is being reduced?
And chlorine is being reduced when it combines with aluminum because it is gaining 3 electrons.
Okay, that's a starting point we have to do first. The next question is, what is the agent? So we're asking about the oxidizing agent. And I'm not sure if these, so a description of oxidizing agent, the substance that gains electrons causes the oxidation. So what it's saying is, in order for something to be oxidized, you have to have the agent that allows it to do that. So if you're in the music business, you have to have an agent that allows you to do that. So it's what is allowing the thing to be oxidized. So then what would we call aluminum in this case? And these terms are a little bit confusing when you first start to get to know them. But remember, the thing I was so excited about before is that everyone said, okay, if we know one is being oxidized, we know the other is being reduced. Because you can't have one without the other. That's what this is basically saying. In order for something to be oxidized, it has to be paired with an oxidizing agent that allows it to be oxidized. If you don't have these two together, this reaction doesn't happen. That means that this one then acts as the reducing agent because it allows the other one to be reduced. That's where the terminology comes from.
Everything is backwards.
Everything is backwards.
Gaining is
Okay,
reducing.
so I think E is fairly similar to what we've been doing. Let's do F really quick. Okay, here is F. What type of reaction is this? I'm going to give you 20 seconds to answer this. Up to 33 responses. Check with your neighbor.
Definitely not precipitation. Definitely not precipitation. That's the good one.
Okay, and I'm closing out.
Yeah, I think it's Redox because O2 is good.
All right, we have a vast majority of people saying that this is an acid-base reaction.
Combustion, because that is.
You're wrong. Okay, why? Let's talk about why really quick. Jay, why did you pick redox?
Okay, well, I picked redox because, well, I eliminated being precipitation because it doesn't form a solid.
No solid formed?
It can be no reaction because it's from a liquid to gas, then to gas. So then
Careful, we could be boiling stuff and it could change states.
right.
But the chemicals are totally different.
Yeah. Okay. Okay. Cool. So. So then, when I looked at like where we were required the acid base, it has to be has to have neutralization, which I didn't see, and then the OH. There was no OH together in one, but then in the end it formed H2O, even though it was labeled a gas. So I picked redox because I don't know. Most commonly it forms H2O, even though it's not labeled liquid.
So here is a huge take home. All combustion reactions are redox. Just remember at the beginning, when we were talking about redox, someone said, why is it called oxidation and reduction? Oxidation is the reaction of a molecule with oxygen gas. And afterwards, oxygen gas is not there. Any combustion, you're burning propane, methane, you're burning any fuel source, cellulose, it's a redox reaction. If it's going to be called combustion, the definition of combustion is O2 combining with the fuel. But it doesn't have to be, you can have oxidation without O2, right? So oxidation is much broader than only combustion reactions. Okay, so in the last couple of minutes, I want to actually jump to the back page. And I want us to shift gears a little bit. The pre-class quiz for Wednesday is about this topic. So I want to give you a little bit of context for it. So when we think about solutions, hopefully one of the first ones that comes to mind is water. Is that usually just pure water that we get in a glass? There's a lot of different stuff dissolved in there, right? And sometimes those things that are dissolved are healthy, electrolytes. Sometimes they're not. Where have you seen that recently? Flint, Michigan. So they have a lot of different stuff dissolved in their water. And lead is one of those. And lead ions are toxic. Especially for children that have developing brains, it's super toxic. There's also algae blooms that happen. So Lake Erie, over the summers, because of a lot of fertilizer runoff, algae grow. They produce toxins, certain ones, and you can't drink the water there as well. So I want us to think about, how do we talk about the amount of these things that are dissolved in solution? What are some of the ways that we talk about how much is dissolved?
Moles, parts per million.
Parts per million, that's a very common environmental one, right? If you're a chemist, maybe moles is how much of the thing is dissolved. Grams. What else?
Ratios,
What kind of ratios?
like how much per like 1 mole of water.
Okay, so if we're talking about, let me take it out of the chemistry sense for a second. We say how sweet is something. That's a ratio. If it's super sweet, it means there's a lot of sugar in a small volume. That ratio is really high for the solute, the thing dissolved, in the solution. We can talk about moles in liters. We can talk about, has anyone been to a bar before?
Oh yeah.
And you look at a bottle and it's ABV. That's the percent volume of the total liquid that is ethanol or alcohol. So that's another form of talking about what the ratio is between the thing dissolved and the thing that it's in. So in this class for Wednesday, we're going to talk about the quantity of solute What are some different measurements? We said grams, we said moles. We talked about the volume or the mass. We can do the same for what it's dissolved in. And the biggest thing that we're going to be starting to shift our focus on is talking about concentration. That's how sweet is it? It's the relative amount of how much is dissolved in the overall amount. And so a simple visual that kind of helps us think about that is if we think about something that's high concentration, we have the same amount of liquid in both, but the thing that's dissolved is in much higher ratio. So your homework for Wednesday, your pre-class quiz, has you working with different ways of thinking about it. Don't get lost in the numbers. It's a ratio. It allows you to go from how many to how much volume. How much volume to how many. In different ways.
I have a question. Did someone leave a charger in the lab? I found this